about it for a little bit, and then we'll do it. You thought I wouldn't ask about it, did you? All right. Hello, YouTube people. There is a quiz. Okay. Okay, all right. Who wants to still think about it? All right, I'll let you think about it for a bit more, and then I'll tell you. Right, so the question here was about whether x is equal or not. So here it says xl is either minus 1 or 1. And what all the options are, like minus 1 or 1. No, just all right, we're still thinking. All right, so what are we trying to do here? So we're trying to minimize this term e, right? Which is minus this sum.
So to remind people, what is the sum? This is just the sum of all kind of x0 times x1 times the two in the middle. This cursor might be too small, but I'm going to move it around so that you can kind of see it. And then you're saying x0 times x1 times the -1. And then you're saying x1 times x2 times the 1, right? So basically all the combination of the nodes, they're all connected. And you're saying, what is the combination of x0, x1, x2 that makes this the smallest? So if you remember, what we're trying to do with the Hopfield nets is we're trying to store memories. And the way we're doing it is we're setting the weights. So we're setting the -1 and the 1 and the 2, for example, in such a way that the actual memories would represent energy minimum. Okay, that's the concept. So, one way to do the multiple choice question is, of course, to just say, well, I'll just plug in the 3 possibilities that are on the quiz. Let me open up the quiz. Quiz 3. Preview. So, the 3 possibilities are like those 3 possibilities. You can just plug every one of those in. The question is, which one leads to the smallest energy? Well, that's not a hard question. The other way to think about it is, well, like what stands out there? Well, what stands out is the weight 2. So you just say, if only I could use the 2 to make the sum really negative. I'm trying to minimize it, right? So to use the 2, what I would do is I would say x0 is 1 and x1 is 1. Right? Because otherwise, like if one of those is -1, then I'm not really using it. I suppose I could do it like with -1 as well. Right? And then I'll ask, x2, what should it be? Well, x2 times x0 is -1. And then x2 times x1 is, like it could be 1, it could be -1. So it could go either way. So what I was going for is just 1, 1, 1. The point is 1 and 1. I think, now that I think about it, -1, -1, -1, -1, 1. No, yeah. So that actually also works. That also works out to 2. So either one of those works. And if I took away your point for the third one, I'll give it back. Okay. So that's that. Questions about this? Is that, yes. Say again? The calculation for the third one, yes. So I will do the calculation for all of them in a few minutes. We'll write code that does it. Okay. All right. Other questions? Okay. Okay. All right. So that's the correct answer. What are we saying? What is the bottom equation referring to? So this equation is the simplified equation from the slides. Essentially, what happens if you ignore the zeros, the b's rather, and you set all of them to 0. So this is minus this sum. Okay, and so you're taking the sum, all the possible xi times all the possible xj times sij, and then you say minus all of that. That's the usual way that people write those things. You could also, of course, say forget the minus and maximize instead. That would be the same. All right. What else are people saying? Yeah, they are. Yeah. So if you did the third, I didn't do multiple possibilities, but I will give you the point. Okay. Okay. Other questions? Okay. Ignore the means. So okay. So I want to first very briefly talk about the midterm that's coming up, and then come back to talk about this. And actually, it kind of happens that Jeff Hinton won the Nobel for that. And it also works really well with the material. So we'll just write some code to solve this exact question in a minute. But for now, I want to talk a little bit about studying for the midterm. So first of all, what's the idea? So the basic idea is you need to be able to do lecture examples and the examples from the labs from scratch. Of course, you're not supposed to know how to have done the examples from lecture before you came to lecture. That's why there is a lecture. But after you look at the examples from lectures and think about them, the ideal is that you would then be able to reproduce those examples from scratch. Now, what you want to do, if you follow this approach of like, I got to know the solutions to the labs, I got to know the solutions to the examples from the lecture, you don't want to like read it and then try it right away, because you don't want just memorization, you want kind of deep understanding. And one way to achieve that without fooling yourself into thinking that you understood, but actually having it be the case that you just memorized, is you want to read it for a bit and then clear your head, do some light distracting work, calculus practice or something, right? Take a walk, and then come back, do it from scratch. Again, kind of in this course, unlike in most other courses, you cannot actually fool yourself if you're not trying to, because if you code something up, you run it on test cases. If it works, it works, right? So in this course, Python provides an immediate check on you on whether the solution is right. Sometimes an approach that I see that I think doesn't work really well is for people to kind of like approximately jot something down and say, well, like good enough. I do that, but I already have a degree. So you really can. Like, it's very easy to fool yourself if you're not actually working and if you're not actually checking that your code works. Okay. There was a question somewhere. Maybe not. Okay. So my promise to you is at least 2 questions. Well, what you count as question is kind of ambiguous, but at least sub-questions, usually a lot more than that if you look at past midterms, will be very connected to what's in the lab. So make sure that you know how to do the labs. Again, the recordings for the solution sessions for everything are on the front page of the course. It's also on YouTube and the same places where the lectures are. So over here, if you like, you can look at past midterms along with solutions and marking schemes. On here, the 23 one, I'll kind of post it like tonight. Okay, but lots of those already. You cannot yet do all of those, but you can, for example, do question 1 through, just because usually the midterm is around Halloween time. And it's, not even Thanksgiving yet. But you can do questions 1 through 4 from 2022, for example. I checked that you can do those. Okay. Of course, skill growth, especially if you're starting from a very low baseline, or if you came here with no background in programming at all, of course, kind of like the skill curve goes like this, right? So the more you know, the more you can learn. And that kind of means that if you look at the midterm that's supposed to come around Halloween way ahead of time, you might freak out because it goes like this and you're here. Okay. Hopefully not you, but like, some people. So look at questions 1 through 4. We will have extra sessions that are on the next slide. Coding Bat. So Coding Bat is posted in the course calendar section. So we already had one kind of practice assignment that you had to do. We will have another one next week that's going to be due before the midterm, but really it's going to be just 15 exercises. That 15 is not very low, but it's still not that much. So if it's hopefully not going to be burdensome and for the people who don't need them, and it's going to be very useful, I think, for the people who do need them, because Coding Bath, so the name Coding Bath comes from like bathing practice, right? So it's about basically practicing basic skills. And those are the sets of problems that they suggest, and the 15 will come from those ones. And I want to remind you again, because like people forget, and I get annoyed by that. This course is about doing problem solving using programming. So what you want is you want to take any real world problem, potentially one that hasn't been solved yet, and solve it using coding. There are often, luckily, techniques that you can use that recur, but this is secondary, right? It's not about memorizing particular Python syntax. It's not about memorizing, particular techniques. It's about learning a skill. The way you learn to swim, the way you learn how to play the piano, the way you learn, most things actually. In part, you get there by practicing. If you play a sport, if you play an instrument, you know that that's how it is, right? It's not about memorizing theory, although there is theory. It's about getting this muscle memory. And that's in part what coding math is about. In part, that can be by thinking through something that's a little bit complicated and getting to the point where you understand it deeply enough that you can reproduce it. Okay, so that's my approach. That is how I try to write the midterm in a way that tests this. Now, in practice, what I will say is make sure you can do the labs, make sure you can do the examples from lecture. Think about things as much as you can. All right. Saturday, Sunday, Monday, this long weekend, we're going to have online sessions. So on Saturday, there's going to be the usual solution session for lab 5. It was, to put it mildly, not well attended yesterday. People's patience for Thursday 6 o'clock sessions might have been wearing out, or you might have had deadlines. So I moved it to Saturday. Sunday and Monday, I'm going to do questions from past midterms live that are accessible right now with the material that you have. And then I'll do it for a while, and then I'll do a Q&A with whatever people want to ask. Yeah. Yeah, so same as the lectures, right? So it's going to be broadcast live, and then I'm also, so I think it's better if I give you the Zoom link, because that kind of the YouTube broadcast is delayed by a couple of seconds, but it's going to also be on YouTube. I'm going to give you a Zoom link to ask questions live if you prefer, or you can use Discord. Okay. All right, so same thing, except on the weekend. Okay. And part of why I'm doing this is I might need to cancel one lecture in November, so making up for that. But you get 3 for free. It's amazing. Okay. So I want to go back to getting the energy minimum of a Hopfield network. As it happens, for a particular Hopfield network, for example, like the one that we just saw, this is not actually hard. So let's do this. There is a question here. So there's a question, I think, about the midterm. So should we be able to do all the questions from the labs? The past few. So here's what I'm going to say. You should ideally be able to do all the questions from the labs. However, the last several questions, while they're solvable using the knowledge that you should have from lecture, they're not easy, which is why they're marked as optional. So for the guarantee of 2 questions from the labs, I'm not talking about the optional exercises. But to get 100, well, sure, you need to demonstrate some kind of problem-solving ability. So that doesn't mean, and in fact, I won't take the optional questions and say, I'm going to put something that's like them, literally. I will, and if you look at the past midterms, most of the way they're designed is some of the questions are basically coding bats, and some of those are like coding bats, like not the hard ones. Some of the questions are more like, the questions from the middle of the lab. And then there is like one question sometimes that's kind of intended to challenge people, because people are not having enough fun during the midterm. Like, I don't want anyone to get bored or anything. Okay. So that's just one question. You will find that it's usually the case that, getting 100 on the midterm in Anxi, it's hard, that it's supposed to be hard. I'm trying to make it so that getting something like an 80 is, completely possible without displaying, anything outside of just understanding what went on in lecture. About 10-15% are, yes, it's a problem-solving question. 10-15%. I know that people are used from high school to getting like high 90s. That's how you get into Anxi. But that is like not the reality of Anxi. There is some problem-solving required. Yeah. Yeah.
Like what was the average last year for your?
The question is, what was the average? I mean, I think the average for the midterm is around an 80, so like high 70s.
Oh.
Yeah. So that's the midterm. So like usually the way it goes is the average for the assignment is quite high. So the average for project 1 was like 85%. And then the average for the quizzes is quite high for obvious reasons. And then the average for the midterm and the exam are a little bit lower. Yeah.
So it's not like you don't need to cover that, like it's okay.
Oh, I often adjust the grades. So it's often the case that the midterm is a little bit more difficult than I predicted, and then I adjust it up a little bit. So I don't, and not many people know, but you're not supposed to curve at the University of Toronto in the technical sense of curve. So you're not supposed to aim for a particular average, and I don't. But what happens sometimes is, I'm aiming for a particular level of difficulty, and then I realize, oh, this question was like harder than I expected. And in that case, the appropriate thing to do is to adjust. Okay, other questions? All right, okay, let's get to coding. So you can look at so there's a question, will we be docked marks for minor mistakes? The answer is, well, there's no semicolons in Python really, but you can look at the marking schemes from previous years. So if you click on the solutions for the midterm, those come along with marking schemes, so you can know exactly what it's like. The answer in general is depends how minor and depends in what context. So if you're solving the problem-solving problem and you like make a small typo, of course, you're not going to care. On the other hand, if it's a question where the answer is like literally 2 things, like 2 words or something, then yeah, like if you get one of them wrong, well, you got to lose some marks for that. And it's also just like, if it's just 2 things, then, well, check your work. So it's kind of like that. You can look at exactly what the marking schemes are on the website. Okay. Other questions? All right. Okay. So AA 3. I like 3.14. I like that number. Okay. All right. So let's go back to this. So let's say that it's not a multiple choice question, but what I want to do is I want to find what the minimum of this network, the energy minimum of this network is. So the strategy that I'm going to use is I'm going to make a function that takes in x0, x1, x2, computes the value of the energy. And then we're just going to try every possible combination of x's. This is exactly what we did the other day, right? So it's exactly the same as trying to list out, like imagine that the password is the answer to the quiz, right? What is the minimum of this network? So that's exactly what we're going to do on a high level. So let's do this. Okay. So this is the network. And what, so I also want the energy. So that's going to be like this. I don't know if I can fit all of those things on the screen at the same time. I'm going to try. Sorry. So this is a little bit annoying. Okay. Here we are. So if I make the type this big, can you see it in the back? Yeah. Okay. So, all right. So we're going to try to compute the energy here. So essentially, we're going to compute this formula. And the input is going to be x0, x1, x2. So this is a big sigma, but if the input is x0, x1, x2 anyways, this is just 3 terms that I need to add up, right? So that's what I'm going to do. I'm going to compute the first term. So that's going to be what? X0 times x1 times 2. Right? So this is x0, x1 times this 2. And I'm going to compute term 2. And well, I have options about what I call it term 2, but let's say that it's this guy. So that's going to be x0 times x2 times -1. And then term 3 is going to be the other one. So x1 times x2 times 1. And then I want to return minus term 1 plus term 2 plus term 3. That's it. That's the energy for this particular network, which is currently hidden, but here it is. Does that make sense? Questions about this? Is there anyone who this does not make sense to? Okay, a few people. So what we're trying to do, problem solving. Here's a problem translated into code, right? So what we're trying to do is we're trying to compute this sum and then take the negative. So this sum is every possible combination of x's, so xi times xj times sij, so times this kind of thing, like the 2. Yeah?
But why are we adding negative? I know it's in the formula, like how is it like?
Okay, so the question was like, why? Sorry, so let me finish the explanation and then I'll get to you. So what we're trying to do is we're just saying all the possible combination of the x's times the weight of the connection, right? And what are all the possible combinations of the x's in this network? Well, it's x0, x1, and x0, x2, and x1, x2. And then we multiply by the actual connections over there. That's all there is to it. Because there's just 3 possible combination of x's, the sigma just becomes term 1 plus term 2 plus term 3. Okay. So to your question, why is this a minus? And this has to do with why this got the Nobel Prize in physics and not in something else. So this kind of network vaguely corresponds to how materials work. And then you can imagine, so materials are composed of particles. One way of thinking about it is the particles interact. And then if, for example, 2 particles repel each other, then they're going to try to repel each other. If 2 particles attract each other, you're going to try to put them together. And then it's going to settle somehow. And it's going to settle into, in some sense, the minimal energy setting. So this kind of corresponds to that, and that's why you want the minimum energy. That's the metaphor. If you didn't understand this, this was a metaphor. If you did, there you go. A Nobel Prize is coming to you in about 40 years. So, all right. So that's like that. And yes, so you're completely right. Like we could say, like, forget about calling this energy. It's a metaphor anyway. Just call it something. And instead of doing the minus, just maximize instead of minimize. Totally could do it. Okay. All right, so now what I want to do is find the minimal energy combination of x0, x1. So how do I do it? So first of all, let me print out all the possible energies. So what is it? Well, it's the same as print all passwords, right? We want to try to print every possible x0, every possible x1, every possible x2, and the corresponding energy. How do we do it? What we did last time, right? So we say for x0 in -1, 1. So the notation, this is a list, right? So x0 is -1, and then x0 is 1. It's not like an interval. And then we're saying for x1, also in -1, 1, and for x2, also in -1, 1. So we can print x0, x1, x2. And we can also print the energy that corresponds to them. So let me make it nice. So I'll say x is like this. Then I'll close the parentheses. So this is just a way of just saying like literally x and then 3 numbers, x0, x1, x2. And then I just print the closing parentheses. Does that make sense? Questions? Okay. And then I'll also print the energy that corresponds to them. So x0, x1, x2. All right. So this is the same example as print all passwords, just applied to this setting. So let me run this. Didn't print anything because I didn't call print all energies. So this is how it goes. So wasn't nice of me to one, 1, 1 is -2. What? So I'll print the energy as well. So here I'm saying E x0. Sorry, I'm a little bit confused by what's going on here. Just 1 second. So here we're saying E is x0, x1, x2, and term 1 is x0, x1, x2. So if I go back here, so x0 times x1, so this is 1, 1, so this is 2. And then, oh, sorry, yeah, this actually makes sense. So 1, 1, 1, yes, it's -2, and that's the smallest energy, right? Because we want the smallest. So the way we figure it out, so we say so we want this, we want the most positive and then negative. So this is going to be 1 times 1 times 2. So the contribution from here is 2. And then the contribution from here is going to be 1, and the contribution from here is going to be -1 if they're all 1s. So that's going to be the maximal possible sigma, and then the minimal minus sigma is minus that. Yeah.
Minimize.
That's right. So
the question says like maximizing, so we're not gonna add the minus.
No, I mean, if it says maximize and then there is a minus sign, then you maximize the minus sign. If it says minimize, so like it's just that maximizing without the minus sign is the same as minimizing with the minus sign. Yeah, there is a question on Zoom. Okay, go ahead. A little bit unorthodox.
I have a
but
question.
Let's try it. Yeah,
Is
go
this
ahead.
stuff on the actual quiz?
Yeah,
With this,
sorry, I
Okay.
cannot actually hear you. Please post it in the chat or in Discord. Oh, maybe you did post it in the chat. Is this well, in a sense, yes, it was on the quiz that was available from 10 past 4 to 30 past 4. So, oh, okay. So, I mean, again, this stuff is nothing special. So I don't want you to think about it as like something extra. In the same way that anything is on the midterm, this could be on the midterm in the sense that you need to understand what is going on in lecture. Yes. So there's four combinations that have the value -2.
Like, so all the options,
Say again?
all the options, they all give the same.
What? Okay, but I'll double check that. But yeah, maybe. Okay. So, all right. So this is printing on all energy. So now what we want to do is we want to minimize the energy, right? So we want to print out one solution that minimizes the energy. So how can we do it? Let me do a simpler example. So if I want the minimum of a list, how can I do it? One way to do it is to go through every possible index and say, is this the minimum? Is this the minimum? Is this the minimum? Right. So I'm going to do it like this. So I'll say current minimum is 0. Sorry. I'll at 0. And the current minimum location is 0. So the idea is I start with saying, maybe I think that the minimum is 0. And then I'll check, is L at 1 even smaller? And if it is, then I'll update the current minimum and the current minimum location. And then I'll do the same thing with index 2 and so on. So I'll say for I in range length of list. So this means in this case, I is 0, I is 1, I is 2. I'll say if L at I is smaller than the current minimum that I've seen, then I want to say current minimum is L at I, and I want to say current minimum location is I. And eventually I'll return current minimum location. Does that make sense? So let's trace it by hand with L equals to 5 minus 2, 10. So initially current minimum is going to be 5, and the location of the current minimum is going to be 0. And then I say, okay, so let's try I equals 1. So when I equals 1, I ask, is L at 1 smaller than the current minimum? In this case, yes, it is. -2 is smaller than 5. In which case, I'll say, update the current minimum to -2. And remember what the location of where you saw it is. I then go to I equals 2. And I say, is list at 2 smaller than the current minimum? No, it's actually larger. So I just don't do any of that. I'm out of the elements in the list. So I'm on line 21 and I'm returning the location of the current minimum. Make sense? So that's what it is. Questions about this? Okay, so let's now apply it to finding the smallest energy. It's the same principle, right? So this was just printl energy. So I'll just copy and paste this and get and call it like retrieve minimal energy. So instead of printing, what I'm going to say is, would this happen to be an x, meaning x0, x1, x2, that corresponds to a smaller energy than what I've seen so far, right? So I need to start with some energy. Here there is kind of, so here it was straightforward. I just said, well, like L at 0 could be the minimum. The first time I try it, then I'll just compare I equals 0 to, sorry, L at 0 to L at 0, and those are equal. And then I'll go to L at 1. Here, I need to start with some energy. So one option is to just do one extra computation and start with the current minimum energy being E at 0, 0, 0. And then I'll do per min x0. And so I used again the keyboard trick. If you don't do it, I'll give you time to type it out the inefficient way, but it's worth practicing a little bit. So those would be just 0, 0, 0. Right? So this is just multiple assignment. This is just like a short way of saying put 0 in Kerman x0 and put 0 in Kerman x1 and put 0 in Kerman x2. And what I'm saying here is that the current the current minimum energy that I've seen is the energy at 0, 0, 0. And the x's that correspond to that are also 0, 0, 0. Right? And then I'll just say, okay, so the current energy here is E at E of x0, x1, x2. And if the current energy is smaller than the minimal energy that I've seen so far, I'll just update. I'll say Kerman energy is equal to current energy. And this stuff, so again, being able to use the keyboard is good. Use the arrows to navigate. Use the arrows to select. Control C, Control V. You can also use lists for this. All right. So at the end, so we can return a list that consists of Kerman x0 and Kerman x1 and Kerman x2. Like so. Right. So retrieving nx from this kind of network that corresponds to n energy minimum turns out to use, well, you could use, this is not efficient, but you could use the same technique to find a minimum of this kind of Hopfield network. So in this case, what you would have, so remember, the way we're using the Hopfield network is in order to store data, approximately. So what we would say is that this network stores the data that correspond to the minima of the energy function. So this stuff and this stuff. So that's kind of cool, because what this means is that we used 3 numbers, right? So we used the 2, the 1, and the -1 in order to store 4 vectors of 3. Now, there are downsides to this as well, but this is kind of the idea, is you have this network that represents multiple memories, possibly more than just the 3 weights to 1, -1. I should say that this kind of thing, it totally works. Like that's what it is. And it runs instantaneously for this kind of network. In practice, if you're hoping to store anything that's larger than that, you're not going to be able to find the minimum of the network in this way. And the reason is there's too many combinations, right? So imagine that the axes go like x0, x1, and so on up to, small stuff. So this is 10 million. So how many possible combinations of -1s and 1s are there here? Anyone know? So 2 to the power of 1,000,001, right? So, which is an extremely large number. And the reason is, well, in order to print out all the combinations, what would you have to do? You would have to write this kind of nested loop with 1,000,000 for loops, 1,000,001, in fact, because you go from 10 million and 1, right? So how many times does this repeat? Well, this repeats twice, and then you repeat twice, the repeating twice. So this repeats 2 times 2 times. And then you repeat twice, the repeating twice again. So this is 2 times 2 times 2 times. You add another for loop. This is 2 times 2 times 2 times 2. So 2 to the power of however many for loops there are is how many combinations there are here. 2 to the power of 10 million. You can try to compute it. So it's 10,000,001. Doesn't work. Also doesn't work. It's not even small enough for Python to be able to store that number. It's really huge. So that means that you're not going to be able to find the minimum using this algorithm. Hopfield figured out something more efficient, about which you can read in the slides that are linked from yesterday. All right, I will see you, if you like, at the solution sessions and the whatever Q&A sessions. And then on Wednesday, if you prefer to not do that. See ya.